On in Chapter 2 now, Topic 2.3, Polynomial Functions and their Graphs. Now, what I'm going to do is give you some general background on polynomials, and that should help us get started. Now, what I have here is algebraic expressions. Well, how do you know they're expressions? Well, because they are algebraic expressions, because they have letters unknown in them. Now, a couple of main things that we want to go over here is this is the quadratic form when you have x to the second power and it's descending. So what is the degree of this term? This degree is the exponent, the sum of the exponents, in this case is only the one variable, on the variable. So the degree of this term is 2. The degree of this term is 1, because there's a 1 there, and there isn't one here. You might think of this as x to the 0, which is 1, but just think of it without a variable. The degree of that term is 0. Now here, the degree is 3, 2, 1, 0. This one is 4, 3, 2, 1, 0. Now, these first three are true polynomials. Now, sometimes things are not a polynomial, even though it might look like one. And what is a polynomial, by the way? It's just an algebraic expression where, and in order to be a polynomial, you can't have any negative exponents. So this would not be a polynomial. You can't have any fractional exponents. This would not be a polynomial. You can't have any variables after you simplify in the denominator. This would not be a polynomial. And you can't have a variable under a radical sign. This is not a polynomial. So again, we're going to be using this, and as we go through this section, we're going to ask, like, what is the degree of the expression, or in many cases, the equation, and then what is the leading coefficient? Now, the leading coefficient is the term with the highest degree. And if you have it in descending order, it'll always be the first. So here our leading term is 3. Leading coefficient, here it's a 4. Here it's a negative 2. Now, depending on the degree, there's going to be various shapes of the algebraic functions. And some are going to start up, some are going to start down, some are going to wavy through things with smooth, and all of this we're going to go over as we give you, again, background material to have you become somewhat knowledgeable about all of these things. So let's go back to our regular board. So we'll go over these objectives in some detail because being acquainted with vocabulary is going to be an important part of this section. So we want to identify polynomial functions. We want to recognize characteristic graphs of polynomial functions. We want to determine what is called N behavior. So that's going to be something you'd want to know about. What does that refer to? Use factoring to find the zeros. Now again, finding the zeros on a graph is where the line will cross the x-axis. That is, in a sense, finding the x-intercepts. And we will identify zeros and their multiplicities. Now, what does that mean? Again, we're going to go over that, but that's one of our background words. Use the intermediate value theorem. Again, something you'd want to know. Understanding the relationship between degree and turning points. Now again, that's that degree we just reviewed. And then graph a polynomial function. So here they're going over the definition of polynomial functions. Looks kind of complicated. We'll stick with what I used in the beginning. All right, graphs of polynomial functions. Now, as you look at various functions, and let me make a couple of graphs here. This is the standard background of a graph. And I think visualizing this really helps here. Now, if a graph is what we call smooth and continuous, then it's going to look like this. And continuous means it just keeps going on in whatever direction it is. I'm going to use the same graph. And this should probably go out this way a little bit here. Smooth and continuous. Now, what would be ones that are not smooth? Well, if you had something like this, and let me get a nice line here. So when they have sharp ends, this would not be smooth. And if you had a dot here and a dot here indicating the ends, that would not be continuous. So again, becoming familiar with vocabulary. Now, for end behavior, what are they talking about? Well, for instance, if you had a graph that looks like this, and I'm not going to put the X and Y axis here, but X and Y axis is in the background. Can you see this is sort of starting high and then ending low? Well, another variety of this might be it starts low and ends high. And all of this will depend upon your leading coefficient. Now, what is the leading coefficient? Again, reflecting what we had said. Well, if you have a function to, let's say, the third degree, your leading coefficient is whatever is in front of this. And if this is a positive, that value, then that's going to tell you that it's going to start usually high. And we had that when we did the parabolas. If A was positive, they look like so. Now, if our leading coefficient is negative, it tends to start low to the left and may go other places, but it starts low on the left. So this is what end behavior is referring to. Well, if that leading coefficient is negative, and it will start low on the left. If it's positive, it's going to start high on the left. And you might say, how would I ever remember these? Well, I'm going to show you a little summation chart here. So the leading coefficient test. Again, there is your expression in descending powers. So if your A term, that is the leading coefficient of the highest degree, is negative, it's going to tend to start low on the left. If it's positive, it starts high on the left. So now let's take a look at that chart that summarizes all of this. So looking at this, and again, I don't expect you to memorize this, but be able to understand it. So what do we have here? Well, here, A is going to be greater than 0. So A is positive. So it's going to start low and go up. Remember, if this was an even, and let's say x to the second would just be a parabola. But if this is an odd degree, again, it's going to start low and then continue to go up. Now, if it's a less than 0, if a is negative, it's going to start high. And again, depending if it's an odd degree, will end up down. And they're kind of showing this arrow this way, arrow this way. Now for this one, it's arrow this way, arrow this way. Now here, again, A is greater, so it's positive. It's going to start high, go down. But if it's an even degree, it's going to continue to end up. So they're showing that as arrow this way, arrow this way. Now, if it's an even degree but negative, it's going to start low, go up, but will also end down. So arrow this way, arrow this way. Again, lots of stuff to remember, but again, if you have the basic items sort of written down somewhere, it's something you can study. Now, in example 1, we're going to use the leading coefficient test to determine the n behavior, which is what we see here is the n behavior. Well, what is our leading coefficient? The leading coefficient is 1. We don't write, and it's positive. And its function is to the 4th degree, as we see here. So what will this look like? Well, as we said, it's even, positive, so it's going to start high and end high. And that's what we see. Now, as we look for the zeros of the function, let's go back one. Where would the zeros be here? Well, let me outline them. Well, our x-intercepts are here, and it's touching here at 0, and it's crossing here. Now, when it actually crosses, this is it will be defined by the word, but when it just touches and doesn't cross, the word we use for that is multiplicity. But we'll see that as we go on, and let's take a look at this as we go to find the zeros. So, for example 2, we're asked to find the zeros of this. We can think of this now as a quadratic equation where we're converting the f of x, which could be replaced by a y. We're going to say the y is 0. So that's what they're showing us here. Now this is a 4-termed expression. How can we factor that? Well, we can factor by grouping, taking the first 2 factors, or first 2 terms, and factoring out a common x squared, we get this. And for the second set of 2 terms, taking out a negative 4, and we see now we have a common factor, and then we put the common factor and then picking up on this one and putting it in a set of parentheses. Now, this one also factors, by the way, and they do it by the square root method. I would suggest you do it by factoring it into its conjugates x plus 2, x minus 2. And you're going to get the same answers, plus or minus 2. So here, as we equate each of these to 0, here we get x is a negative 2. Here x is a negative 2, which is a repeat, and x is a 2. So we have a negative 2 and a 2. All right, let's see what that looks like now. And there is one value, and there is the other value. Now, you notice that there were two negatives 2's. So we get multiplicity. When we have multiplicity, it doesn't cross the line, but in a sense bounces off of the line, as is shown here. Okay, now later we're going to find the y-intercept here very shortly. And we see it's going to be a negative 8. Let's just do that here while we're on this slide. That if x, or I should say, yeah, x here is a 0, this would then be a 0, this would be a 0, this would be a 0, y equals negative 8. That's how we get our y-intercept. So if we were graphing this, again, points along this curve. And here we see it defined now, multiplicity and the x-intercepts. If our value is a 0 of even multiplicity, that is, it's going to go x equals negative 2, x equals negative 2, that instead of crossing, it just turns around and in a sense bottoms off of the, or tops off, depending where it's located, the x-axis as I just described. Okay, let's go on. Now, finding the zeros and their multiplicity. This is example 3. So here is a factor, and here is a factor. And again, if we want to find the zeros, we're going to use that zero factor principle that all of this has to equal 0, or this factor has to equal 0. And we'll see it worked out on the next slide. So again, we're separating them into their factors, and we take the square root of this side. We just get x plus 1/2 equals 0, and then transpose the 1/2 to the other side. So one of our zeros, remember, since it's squared, this has two values, both the same. So this shows multiplicity at negative 1/2. It's not going to cross the line. It's just going to bounce off it. And multiplicity of 2, because this was to the second degree. Now, this other one is going to show x equals 5 as a 0. Remember, this is an ordered pair. This is x is 5, an x-intercept, and multiplicity of 3, because this was to the third degree. So continuing example 3, here is the graph of this. And it would be something to be able to put all the points and then sketch it. But notice here at 1/2, negative 1/2, there's a multiplicity of 2. And here at 5, now the graph crosses here, but there is a multiplicity of 3 at this point. That is a 0. Now, you might say, why is this one bouncing off? Again, that's an even multiplicity. Odd or 3 in this case, multiplicity actually crosses the line. It's only even when they bounce off and don't go through the line. Continuing with our vocabulary building, the intermediate value theorem. All right, let f be a polynomial function with real coefficients. If a and b have opposite signs, let's say a is negative and b is positive, then there is at least one value of c, which we'll put between these, for which c is equal to 0. That is, it will either touch or cross the x-axis. Eventually, the equation, which is what we've been talking about, y is 0, has at least one real root. All right, let's take a look at that. And we'll clear this up and go on to see it illustrated here. Okay, so this is example 4, where we're going to say we have a 3, a negative 10, and a 9. And let's say if there is a real 0 between these two values. So this one is a negative 3, negative 2. So we put in a negative 3 substituting in here, and we end up with a negative 42. Now we put the negative 2 in this one, same equation, substitute, and we get a 5. Now notice then our A term would be a negative 42, and our B value is a 5. So opposite signs, there is a value C between them that would indicate a point which would be a 0 that is crossing the x-axis, an x-intercept. Now let's see what this looks like in our next slide here. We'll clear this up. Now, there are two ordered pairs that we've picked out. And notice right here, between where this one is and where this one is, the curve, the line, is crossing the x-axis, and that's an x-intercept. Okay, that's all they're trying to say here, as using the intermediate value theorem. In this slide, they're featuring turning points of a polynomial function. Here's the definition. In general, if f is a polynomial function to the degree n. So, polynomial, if it's going to be a quadratic, which is 2, 3, 4, 5, these are the degrees. How many places will the curve turn? That's what they're saying here. And the formula for this is going to be n minus 1. So if it was a polynomial to the second degree, it's going to have, that would be 2. So 2 minus 1 is going to have 1 turn. If it's to the third degree, remember we said these look like this. So our degree is 3. 3 minus 1 is going to turn twice, there and there. And that's what this refers to. So hopefully something easy here. Now in this slide, it goes through the strategy for graphing polynomial functions. And it's quite detailed. And again, I'm not going to read this to you. You can pause it, look it over, and it should make sense. It's kind of bringing all of the things we've talked about so far into this summation. Let's go on to take a look at it. Now, we're going to go through the 5 steps in some detail. So number 1, determine the behavior of it. Well, here we see that our A value here is positive. It's to the second degree here, but keep in mind there's also another degree there. So this is actually, this is in its factored form, so it'd be actually to the third degree. So we know it's going to be coming up from the bottom, curving somewhere in here, and then moving up in this direction. Okay? So our A term is positive, and it's to the third degree, and it leads to this. Let's go on. Now, finding the intercepts, that is the zeros. Now, since this is in its factored form already, we can take each of these factors and equate it to 0. So this factor equals 0 here. This factor equals 0. So here we're going to get 2 of the same. And notice we get multiplicity because of the 2. And it's going to bounce off the x-intercept at -2. And then here it shows multiplicity of 1. So it's going to actually cross the x-axis at 3. All right, let's take a look at that. I'm kind of excited about this here. Now, to speed things up here, we're going to take a look too at the finding the y-intercept. So if x now is 0, we put a 0 there and a 0 there, and we get then this is going to be a -2 that's squared. This becomes 2 times 4 times a -3. We're going to get our y-intercept at 0, -4. So there's our -2's bouncing off. It crosses at -24, and it goes through at 3. Excellent. And let's continue. And in part F of example 5, we can use symmetry to help draw the graph, knowing it's going to swing up, and this is what it looks like. And to wind this up, we can check the maximum number of turning points. Remember, this was to the third degree. There's a 2 and a 1 made it to the third, and it's n minus 1 turns twice. All right.